So far, we have discussed the ideal Rankine cycle and the Rankine cycle analysis in terms of thermodynamics and so on. So let's try to solve this example problem to understand better about how to do the thermodynamic analysis for the ideal Rankine cycle and actual Rankine cycle. So please give a pause of this video lecture and read this statement carefully and think about how to tackle this problem. Alright, so let's try to read this statement together. So now we have a steam power plant which operates on the simple ideal Rankine cycle. In reality, that shouldn't happen, but now let's assume that your steam power plant is based on the simple ideal Rankine cycle. Now, steam enters the turbine at 10 megapascal and 500 degrees Celsius. Okay. So we already know the inlet condition of steam that comes to the turbine. And also, that is condensed in the condenser at a pressure of 50 kilopascal. So we have high pressure line of 10 megapascal and low pressure line at 15 kilopascal. Now we want to calculate the net work and the thermal efficiency. Now, I already showed you the TS diagram of this ideal Rankine cycle, but again, I really hope that and I really assure you that you should be able to draw the TS diagram of Rankine cycle. Okay, and now here we go. We have TS diagram. We have high power pressure line at 10 megapascal and low pressure line at 50 kilopascal. And now we assume that we start the first state from the saturated liquid at 50 kilopascal, and we have pump and heat addition, expansion, and condenser. So if you look at the given condition, we know here at 3, because we at 10 megapascal in the pressure and 500 degrees Celsius in the temperature. But because we already assumed that your Rankine cycle is an ideal, that means the pressure at 2 right after pump process is also the same pressure as 10 megapascal. So we know P2 and P3. And we also know P4 and P1, constant pressure at 50 kilopascal. Now, in order to calculate the net work and the thermal efficiency, again, what you have to do is that we have to find out enthalpy values at all states. So we let's talk about each state to calculate those values. Now, in state 1, what you know is pressure and its a state. So by using this given condition, let's try to look at the properties. At 50 kilopascal, what you can see is that we have specific volume, and we don't have to worry about the internal energy, but we need enthalpy. And even though we don't need it, but still there we can find also the entropy. Okay, so let me write those values here. Now that we know H1, that is saturated liquid at 50 kilopascal, that is 340.54 kilojoule per kilogram. And also we know the specific volume at 1, that is this, and we know 0.001030 meter cubic per kilogram. So that is the properties at state 1. Then how about at state 2? What we do know is we know the pressure, which is at 10 megapascal, and we have to satisfy that isentropic process or ideal case. So from those conditions, what you can see is from the ideal Rankine cycle analysis, the pump work can be calculated by V1 times P2 minus P1. Again, that equation is only valid for the isentropic ideal pump work. Okay. Now, we already know V1 and we also know P1 and P2. So from this equation, we can easily calculate the ideal pump work that is given as calculate to be 10.25 kilojoule per kilogram. Okay. But then how can you calculate the enthalpy at 2 at the exit of a pump? Okay. So now the pump work, which is written as V1 times P2 minus P1, but at the same time this pump work should satisfy the enthalpy difference H2 minus H1. So from this relation now H2 can be written as H1 plus pump work. So yes, we can get this value of H2. We have 350.79 kilojoule per kilogram. Okay, so that is pretty unique procedure only for the Rankine cycle analysis. So I really want you to understand this process where we have to use V1 times P2 minus P1 as the ideal pump work. Now, in the state 3, okay, we know P3 and we know T3. Okay. So, by using the table, but by having these two values, we can go to this superheated vapor table where we can find out 10 megapascal for pressure. But right next to 10 megapascal, that is saturated temperature. And the given temperature of the water, steam, that is higher than the saturated temperature at that pressure. So we can clearly see that your state of the steam is superheated steam. And then at 10 megapascal and 500 degrees Celsius, what you can find is that we know specific volume and enthalpy and the entropy. Particularly the enthalpy and entropy are the important properties that we have to use. Okay, then let me write it down here. Now H3 can be written as 3375.1 kilojoule per kilogram. Okay, and we know also S3, which is 6.5995 kilojoule per kilogram Kelvin. Okay, then we can go to state 4. And what we know is we know P4, that is 50 kilopascal. Okay, and now another relation that we have to use is that during this expansion process we have to maintain the entropy. Okay, so what we know is S4 should be same as S3. Then what you have to clearly think about is now where this point is located. Is that saturated liquid vapor mixture or is it a superheated vapor? So in order to tell that, we have to compare the value of entropy at 4 with the saturated vapor entropy at 50 kilopascal. So let's go back to the table. Okay, so table A-5 at 50 kilopascal. Okay, now we see the saturated vapor entropy is at 7.5931, which is bigger than the entropy at state 4. Okay, so it tells us that your point 4 should be located inside the saturation dome to be saturated liquid vapor mixture. So now what it can do is we have to use the saturated vapor mixture equation, which is SF plus X4 and SFG. Now we can find out this value from the table. We can find out this value also from the table at 50 kilopascal. So what it can do is we can calculate the quality. Okay, so X4 can be calculated from the above equation to be 0.8472, and as a result we also can calculate H4 by HF plus X4 times HFG. Okay, and also these values are found from the table at 50 kilopascal, and from this equation we know that this one is 22 93.1 kilojoule per kilogram. So by working through the state 1 through all the way 4, we know the all enthalpy values at each state. So the remaining step is quite simple because the net work can be calculated by turbine work minus pump work. We already calculated pump work, but how can we calculate turbine work? And this turbine work can be calculated by H3 minus H4 minus pump work. So this value calculated to be 1082.0 kilojoule per kilogram. So as a result, we can calculate the net work as 1071.75 kilojoule per kilogram. And now thermal efficiency can be defined as W net divided by Q in, right? So Q in also can calculate by H3 minus H2, which gives us 3024.31 kilojoule per kilogram. So the thermal efficiency is calculated as the value of 0.354 or 35.4%. Okay, so that is how we can calculate the net work and the thermal efficiency of the ideal Rankine cycle. Then let's think a little more about what would happen when this Rankine cycle becomes more realistic. Okay, again, please give a pause of this video lecture and please try to read this statement. There are many loss factors, and please think about how to tackle those loss factors to calculate the realistic Rankine cycle calculations. All right, so now let's try to look at what kind of loss factors are given. So we have pump outlet pressure still at 10 megapascal, okay? But in the boiler, and also the turbine outlet pressure is 50 kilopascal. So baseline pressures are still remain the same. However, we have a heat and pressure losses in the boiler, okay, because of friction and certain heat loss. So steam pressure and temperature after boiler process and at the inlet of turbine are not 10 megapascal and 500 degrees Celsius anymore, but it is 9 megapascal and 450 degrees Celsius. So now we are around here, okay? That is P3, which is 9 megapascal, and T3, which is 450 degrees Celsius. In addition, the inlet pressure of saturated water is 40 kilopascal, and it comes to the turbine, not turbine, pump. Okay, so your steam flows into the condenser at 50 kilopascal, but because of pressure loss, this heater, the water goes out of condenser at 40 kilopascal, so 10 kilopascal loss. So now instead of this one, we probably have around here. So that is P1, and it is 40 kilopascal. Okay, and also we have isentropic efficiencies of the turbine at 90% and also for the pump at 85%. So that is what we know. So that is turbine efficiency, and that is pump efficiency. So still we want to calculate the net work and the thermal efficiency. Again, we have to calculate enthalpy values at all points, like 1, 2, 3, and 4. But because there are loss factors, then we have to consider all these things. Particularly, we have to think about how to use the isentropic efficiencies for a pump and a turbine. Okay, so with that being said, let's try to calculate the state 1. Then we are going to follow all the kind of almost same procedures as we did for the ideal Rankine cycle analysis. Okay. So at state 1, we know P1 at 40 kilopascal and still saturated liquid. Okay. So from the table, we can find out V1. right, as 0.001026 meter cubic per kilogram, and also H1 can be found from the table at 317.62 kilojoule per kilogram. And now state 2, what you know is we know P2 at 10 megapascal, and we know the pump pressure, pump efficiency is 85% or 0.85. So in the case, what you have to think about is how we can use this pump efficiency. Now, in order to give you an answer, when you try to use the pump efficiency, first thing, and also turbine efficiency, and even compressor efficiency, first thing that you have to do is to calculate first the ideal condition. Okay, then from the ideal condition that we can go to the real condition, right? So now, let's try to use WPS as the ideal pump work. Then how can you calculate the ideal pump work for that case? Still the same thing. Then we have to use V1 times P2 minus P1. So that is the ideal pump work that you can calculate. So that is given as 10.21 kilojoule per kilogram. Okay. Then we are ready to use the pump efficiency. So pump efficiency is given as ideal pump work divided by actual pump work, right? And let's say that then we don't have to write the old WPS because you already know the number, and actual pump work can be calculated by H2A minus H1. Okay, here H2 is 2A is the realistic exit condition of the pump. So from this relation, now WPA can be calculated as WPS divided by pump efficiency, which is 12.01 kilojoule per kilogram. And also H2A can be calculated by H1 plus WPS divided by, right? So that is 329.63 kilojoule per kilogram. Again, calculating state 2 is a little complicated, particularly when you really think about the Rankine cycle. Okay, but I really want you to be familiar with this process. And now at state 3, we know the pressure and temperature. So that is on each task. So we know that is 9 megapascal and T3 is 450 degrees Celsius, and from the table we know H3 value at 3258.0 kilojoule per kilogram and S3 to be 6.4872 kilojoule per kilogram Kelvin. Then state 4. Okay, and state 4 we know P4, which is 50 kilopascal, and we know the turbine efficiency at 90%. Again, we have to use this turbine efficiency, and in order to use that turbine efficiency, we have to first calculate the reversible process first. Now, in the reversible process, the entropy at the exit is same as at 3. Now, by comparing the saturated vapor entropy and the value we found from state 3, then you can easily find that this S3 is smaller than the saturation vapor entropy at 50 kilopascal. Okay, so we can calculate the quality by using the same equation as we wrote down before. Okay, but I'm going to use 4S to emphasize that that is really the reversible process, and SFG at now 50 kilopascal. So from this equation, we can calculate X4S, that is 0.8299. So H4S can be calculated as this equation, right? Then still at 50 kilopascal, and we can find out those HF value and HFG value, and from this equation we can calculate H4S, which is 23.2 kilojoule per kilogram, right? So then we are ready to use the turbine efficiency, because turbine efficiency is defined as actual turbine work divided by actual reversible isentropic turbine work. So actual turbine work can be calculated as N eta T, and WTS can be calculated by H3 minus H4S. And so that gives us 904.32 kilojoule per kilogram. Okay. We don't really, also we can calculate the H4A using the same equation as the same way as we did for the state 2, but we don't really need that H4A because we already calculated the WTA, which is actual turbine work, and that is what you want to calculate, right? Okay, so then we are ready to calculate net work, which is turbine work, but actual turbine work minus actual pump work. Okay, so that is 892.31 kilojoule per kilogram. And in terms of thermal efficiency, we know the same equation, and Q in can be calculated by H3 minus H2A, right? And that gives us 28.37 kilojoule per kilogram. So your thermal efficiency for the realistic Rankine cycle gives us 0.305 or 30.5%. Okay. Now let's take a look at all entire calculation process that we did for actual case and the ideal case. Okay, so now what is important is that you have to calculate or find all enthalpy values at and all components, all points like 1, 2, 3, and 4. Then you can calculate the net work and thermal efficiency. So you have to focus on how you can find or calculate enthalpy values. Okay, and the details are still all the same as what we have learned so far by using the table. Okay, so I'm not going to repeat them again, but that is very important now to combine everything together to be able to do the thermodynamic analysis for the ideal and realistic Rankine cycles. Okay, now before I finish this lecture, let's take a look at the answers. Okay, then we can compare the ideal case and the actual case. And obviously, for pump work, ideal needs smaller work than the actual case. And for the turbine, ideal case generates more power, more work than actual case. Okay, so as a result, we have more net work for the ideal case. And also, when you think about it, when you calculate the thermal efficiency, ideal thermal efficiency is way higher than the actual efficiency of the actual Rankine cycle. Okay, so that is why actual case degrades the net amount of power and the thermal efficiency because of many loss factors. In today's lecture, we talked about the Rankine cycle as the base thermodynamic cycle for vapor power plant. So the Rankine cycle, a simple Rankine cycle, is composed of a pump, steam generator, steam turbine. So we also learned the TS diagram of the simple Rankine cycle. And I really hope that you should be able to draw this TS diagram, which is very important. Also, we went through the Rankine cycle analysis to see how we can apply the thermodynamics for an open system to understand what's going on inside the Rankine cycle, and also we use those equations to calculate the net work and also the thermal efficiency of the ideal and actual Rankine cycles. So in the next lecture, we are going to expand that base Rankine cycle to get more power and better efficiency. Thank you so much for your time and your attention. And have a wonderful day, and see you later. Bye.